The title of this module is Properties of Ring Homomorphism. In the study of groups, we had seen the concept of a homomorphism turned out to be a fruitful one. This suggests that the appropriate analog for rings could also lead to important ideas. To recall, in groups, a homomorphism was defined as a mapping such that phi of AB equal to phi of A into phi of B. Since a ring has two operations, the upcoming definition is more natural extension of this formula. First, let us see the definition of a homomorphism. A mapping phi from the ring R into the ring R dash is said to be a homomorphism if the first condition is phi of A plus B equal to phi of A plus phi of B, and the second condition is phi of AB equal to phi of A into phi of B for all A and B in R. As in the case of groups, let us again stress here that the plus and dot occurring on the left hand sides of the relations in 1 and 2 are those of R, whereas the plus and dot occurring on the right hand sides are those of R dash. Let us see some examples here. Phi from Q plus dot to Q plus dot by phi of x equal to x is a ring homomorphism. The mapping defined by phi of xy z equal to z is a ring homomorphism from z cross z to z. A useful observation to make is that a homomorphism of one ring R into another R dash is if we totally ignore the multiplications in both the rings, at least a homomorphism of R into R dash where we consider them as abelian groups under their respective additions. Therefore, as far as addition is concerned, all the properties about homomorphisms of groups carry over. Next result is, if phi is a homomorphism of R into R dash, then phi of 0 equal to 0 dash and phi of minus A equal to minus phi of A for every A in R. Here 0 and 0 dash are the additive identities of R and R dash respectively. Proof is, we have phi of x plus 0 dash equal to phi of x, that is equal to phi of x plus 0 equal to phi of x plus phi of 0. So, by cancellation we get phi of 0 equal to 0 dash. To prove the second one, we note that 0 dash equal to phi of 0, that is equal to phi of A plus minus A, that is equal to phi of A plus phi of minus A. That is, phi of minus A is the additive inverse of phi of A. Some properties of ring homomorphisms. Let phi be a ring homomorphism from a ring R to a ring S. Let A be a subring of R and let B be an ideal of S. First one is, for any R in R and any positive integer n, phi of nr equal to n into phi of R and phi of R power n equal to phi of R the whole power n. Second one is, phi of A equal to set of all phi of A such that A in A is a subring of R. Phi of A equal to set of all phi of A such that A in A is a subring of S. Third one is, if A is an ideal and phi is onto, then phi of A is an ideal. Fourth one is, phi inverse of B equal to set of all R belongs to R such that phi of R belongs to B is an ideal of R. Fifth one is, if R is commutative, then phi of R is commutative. Sixth one is, if phi is an isomorphism from R onto S, then phi inverse is an isomorphism from S onto R. Now, let us see some theorem based on ring homomorphism. The statement of the theorem is, suppose that R and S are rings with identity and that phi from R to S is a surjective ring homomorphism. Then phi of 1R equal to 1s. Here 1R and 1s are the multiplicative identities of R and S respectively. Proof of the theorem is, we have 1R equal to 1s into phi of 1R. Since phi is surjective, there exists some R in R such that phi of R equal to 1s. That is, phi of 1R equal to phi of R into phi of 1R. Since phi is a homomorphism, phi of R into phi of 1R equal to phi of R into 1R. That is equal to phi of R, that is equal to 1s. Next theorem states that suppose R and S are integral domains and that phi from R to S is a ring homomorphism. Then either phi of 1R equal to 0s or phi of 1R equal to 1s. If phi of 1R equal to 0s, then phi of R equal to 0s, and for all R belongs to R. Here 1R, 0s and 1s are the multiplicative identities of R, additive identity of S and multiplicative identity of S respectively. Proof is, we have 1R into 1R equal to 1R. That is, phi of 1R into 1R equal to phi of 1R into phi of 1R, that is equal to phi of 1R, which implies phi of 1R into phi of 1R minus 1s equal to 0s. Since R and S are integral domains, phi of 1R equal to 0 or phi of 1R minus 1s equal to 0s. That is, phi is a trivial homomorphism or phi of 1R equal to 1s. One important remark is, if both R and R dash have the respective unit elements 1 and 1 dash for their multiplications, it need not follow that phi of 1 equal to 1 dash. For example, consider the trivial homomorphism from the collection of integers z to z. Here phi of 1 equal to 0. Another example is, consider the homomorphism phi from z2 to z6 by phi of x equal to 3x for all x in z2 is a ring homomorphism, but phi of 1 equal to 3. However, if R dash is an integral domain or if R dash is arbitrary but phi is onto, then phi of 1 equal to 1 dash is indeed true. In the case of groups, given a homomorphism, we associated with this homomorphism a certain subset of the group which we called the kernel of the homomorphism. After all, the ring has two operations, addition and multiplication, and it might be natural to ask which of these should be singled out as the basis for the definition. However, the choice is clear. Built into the definition of an arbitrary ring is the condition that the ring forms an abelian group under addition. The ring multiplication was left much more unrestricted and so, in a sense, much less under our control than is the addition. Next, let us see the definition of kernel. If phi is a homomorphism of R into R dash, then the kernel of phi denoted by ker of phi is the set of all elements A in R such that phi of A equal to 0, the 0 element of R dash. Let us prove that kernel forms an ideal in this lemma. If phi is a homomorphism of R into R dash with kernel of phi, then the first condition is kernel of phi is a subgroup of R under addition, and the second one is if A belongs to kernel of phi and R in R, then both AR and RA are in kernel of phi. Proof is, Since phi is a homomorphism of an additive group R into an additive group R dash, the condition 1 follows directly from the group theory module. To prove the second part, suppose that A in kernel of phi R in R, then phi of A equal to 0. So that phi of AR equal to phi of A into phi of R equal to 0. That is, phi of AR equal to 0. Similarly, phi of RA equal to 0. Thus, by defining property of kernel of phi, both AR and RA are in kernel of phi. Before proceeding, let us examine these concepts in certain examples. Let R and R dash be two arbitrary rings and define phi of A equal to 0 for all A in R. Trivially, phi is a homomorphism and kernel of phi equal to R. Let R be a ring, R dash equal to R, and define phi of x equal to x for every x in R. Clearly, phi is a homomorphism and kernel of phi consists only of 0. Let j of root 2 be all real numbers of the form m plus n root 2, where m and n are integers. J of root 2 forms a ring under the usual addition and multiplication of real numbers. Define phi from j of root 2 to j of root 2 by phi of m plus n root 2 equal to m minus n root 2. That is, phi is a homomorphism of j of root 2 onto j of root 2 and its kernel of phi consists only of 0. Let j be a ring of integers, jn the ring of integers modulo n. Define phi from j to jn by phi of A equal to remainder of A on divided by n. Phi is a homomorphism of j onto jn and that the kernel of phi consists of all multiples of n. Let f be the set of all continuous real valued functions on the closed unit interval. F is made into a ring by the usual addition and multiplication of functions. That is, a ring is a consequence of the fact that the sum and product of two continuous functions are continuous functions. Define phi from f to r by phi of f of x equal to f of 1 by 2. Then phi is a homomorphism of f onto R and its kernel consists of all functions in R vanishing at x equal to 1 by 2. All these examples given here had used in commutative rings. Many beautiful examples are also exist for non-commutative rings. Now, let us see the definition of an isomorphism. Let R and R dash be a rings and phi from R to R dash is a map. We say that phi is a ring homomorphism if the first condition is phi is a ring homomorphism and second one is phi is a bijection. We say that two rings R1 and R2 are isomorphic if there exists an isomorphism between them. Until now, we know about kernel and homomorphism. By using these two, we can easily find whether the homomorphism is isomorphism or not. That is, the next we are going to discuss the lemma. The statement of the lemma is the homomorphism phi of R onto R dash is an isomorphism if and only if kernel of phi equal to singleton 0. Proof of the lemma is if phi from R into R dash is an isomorphism, then kernel of phi equal to singleton 0. Because kernel of phi equal to singleton 0 for all 1-1 homomorphism. Conversely, if phi from R into R dash is not an isomorphism, that is, phi is not 1, 1. That is, there exists x not equal to y in R such that phi of x equal to phi of y. Since x not equal to y, x minus y is not equal to 0. Then f of x minus y equal to f of x minus f of y equal to 0. Hence, x minus y belongs to kernel of phi. So, kernel of phi not equal to singleton 0. Once the idea of a homomorphism and its kernel have been set up for rings, based on our experience with groups, it should be fruitful to carry over some analog to rings of the concept of normal subgroup. Once this is achieved, one would hope that this analog would lead to a construction in rings like that of the quotient group of a group by a normal subgroup. Fortunately, all this can be done thereby providing us with an incisive technique for analyzing rings. The first business at hand then seems to be to define a suitable normal subgroup concept for rings. With a little insight, this is not difficult. If we recall, normal subgroup eventually turned out to be nothing else than kernels of homomorphisms, even though their primary defining conditions did not involve homomorphisms. Next one is the relation between quotient rings and homomorphisms. The definition of quotient ring is, if R is a ring and I is a two-sided ideal, then the quotient ring of R mod I is a group of quotients R by I with the operations of coset addition and coset multiplication. For example, consider the ring of integers Z and the ideal 6Z. Then the corresponding quotient ring is Z by 6Z equal to Z6. Now, let us see some remarks. The first remark is, if R is commutative, then so is R by I. For A plus I into B plus I equal to AB plus I, that is equal to BA plus I equal to B plus I into A plus I. Second remark is, if R has a unit element 1, then R by I has a unit element 1 plus I. Third remark is, there is a homomorphism phi of R onto R by I given by phi of A equal to A plus I for every A in R whose kernel is exactly I. We summarize this remark in the following theorem. The statement of the theorem is, let I be an ideal in a ring R. The mapping phi from R to R by I given by phi of A equal to A plus I is a surjective ring homomorphism with kernel I. Proof of the theorem is, the fact that phi preserves addition and multiplication follows from the definition of addition and multiplication in R by I. It is surjective since any coset A plus I is the image of A in R. Finally, the kernel is the set of all A in R such that phi of A equal to 0 plus I, the 0 element of R by I. But A plus I equal to 0 plus I if and only if A in R. Thus, the kernel is just I. We can generalize this idea of ideals and kernels to any ring homomorphism. The statement of the next theorem is, let phi from R to S be any homomorphism of rings. Then kernel of phi is an ideal in R. Proof of this theorem is, we know 0 belongs to kernel of phi. So, kernel of phi is non-empty. Let A and B belongs to kernel of phi. Then phi of A equal to phi of B equal to 0. So, phi of A minus B equal to phi of A minus phi of B, that is equal to 0. For any A in R, phi of RA equal to phi of R into phi of A, that is equal to phi of R into 0 equal to 0. Similarly, phi of AR equal to phi of A into phi of R equal to 0. Thus, A minus B, RA and AR are also in kernel of phi. Hence, kernel of phi is an ideal. When phi from R to S is a surjective homomorphism, we say that S is a homomorphic image of R. We next see that every surjective homomorphism really acts just like R to R by I. Finally, we came to the main part of this session, which is the isomorphism theorems. Now we are going to prove the first isomorphism theorem. The statement of the theorem is, let phi from R to S be a surjective homomorphism, that is both onto and homomorphism. Then R by kernel of phi is isomorphic to S. That is, the domain by kernel of phi is isomorphic to codomain. Proof of the theorem is, first we have to define a function f from R by kernel of phi to S by f of R plus kernel of phi equal to phi of R for all R in R. Since we are defining this function, we have to first prove that the function is well defined. For that, we take two elements R plus kernel of phi and T plus kernel of phi in R by kernel of phi. So, let R plus kernel of phi equal to T plus kernel of phi. This implies R minus T belongs to kernel of phi. This implies that phi of R minus T equal to 0. Now, phi of R equal to phi of R minus T plus T. So, that is equal to phi of R minus T plus phi of T, that is equal to phi of T. So, the function is well defined. Now, to prove that the function f is a homomorphism. For that, we prove two conditions. The first condition is f of R plus kernel of phi plus T plus kernel of phi equal to f of R plus kernel of phi plus f of T plus kernel of phi. And the second condition is f of R plus kernel of phi into T plus kernel of phi equal to f of R plus kernel of phi into f of T plus kernel of phi. First, we prove the first condition. F of R plus kernel of phi plus T plus kernel of phi equal to f of R plus T plus kernel of phi. Since f of R plus kernel of phi equal to phi of R, by applying this, we get f of R plus T plus kernel of phi is same as phi of R plus T. That is equal to phi of R plus phi of T. That is equal to f of R plus kernel of phi plus f of T plus kernel of phi. The second condition is f of R plus kernel of phi into T plus kernel of phi. That is equal to f of RT plus kernel of phi. That is equal to phi of RT. Since f of R plus kernel of phi equal to phi of R. So, that is equal to phi of R into phi of T. That is equal to f of R plus kernel of phi into f of T plus kernel of phi. So, we say that f is a homomorphism. Now, to prove f is onto. We know that phi is onto. For S belongs to S, there exists R belongs to R such that phi of R equal to S. Since phi of R equal to f of R plus kernel of phi, therefore we get f of R plus kernel of phi equal to S. Therefore, f is onto. Next, we prove f is 1, 1. It is enough to prove that kernel of f equal to 0 in R by kernel of phi. If f of R plus kernel of phi equal to 0, then phi of R equal to 0. This implies that R belongs to kernel of phi. So that R plus kernel of phi equal to 0 plus kernel of phi. Therefore, F is 1, 1. Hence, we prove that F is homomorphism, F is onto, and F is 1, 1. Hence, F is an isomorphism. Therefore, we say that the domain by kernel of phi is isomorphic to codomain, which is the first isomorphism theorem. Next, we are going to see the second isomorphism theorem. The statement of the theorem is, let I and J are ideals of a ring, then I by I intersection J is isomorphic to I plus J by J. Here is a picture showing the inclusions. The double lines represent the two factor rings. The proof of the theorem is, we define a function phi from I to I plus J by J by phi of I equal to I plus J. Here we use the first isomorphism theorem to prove this theorem. By the first isomorphism theorem, we have the domain by kernel is isomorphic to codomain. So, proving this, it is enough to prove that kernel of phi equal to I intersection J. For that, we take one element I belongs to kernel of phi. So, by the definition of kernel of phi, we get phi of I equal to 0 in I plus J by J. The 0 in I plus J by J is also J. From this, we get I plus J equal to J. That is, this which implies I belongs to J. Since I belongs to kernel of phi and I belongs to J, we get I also belongs to I. So, since I belongs to I and I belongs to J, we get kernel of phi equal to I intersection J. From this, we say that I by I intersection J is isomorphic to I plus J by J. Next, we are going to prove the third isomorphism theorem. The statement of the third isomorphism theorem is, let I and J be ideals of R and I subset of J. Then J by I is an ideal of R by I and R by I by J by I is isomorphic to R by J. Here also we define a function phi from R by I to R by J by phi of A plus I equal to A plus J. We can easily prove that phi is a surjective homomorphism. That is, phi is onto an homomorphism. We can also easily verify that J by I is an ideal of R by I. Now, by using the first isomorphism theorem, domain by kernel is isomorphic to codomain. So, as in the previous theorem, we can verify that kernel of phi equal to J by I. So, we take one element belongs to kernel of phi. Let A plus I belongs to kernel of phi. By using the definition of kernel of phi, we have phi of A plus I equal to 0 in R by J. The 0 element in R by J is J. From this, we say that A plus J equal to J. This implies A belongs to J. Hence, kernel of phi equal to J by I. Since I is a subset of J. So, R by I by J by I is isomorphic to R by J. Now, we are going to prove another theorem called the correspondence theorem. The statement of the theorem is, let R be a ring and U an ideal of R. Then there is a one-to-one correspondence between the ideals of R which contains U and the ideals of the quotient ring R by U. In order to prove this theorem, we consider two sets. The first set is C be the collection of ideals of R containing U and let D be another set which is the collection of ideals of R by U. We define two functions f and g. The first function f from C to D which is defined by f of j equal to set of all a plus u such that A belongs to J, which is a subset of R by U. And we define another function G from D to C by G of I equal to set of all A such that A plus U belongs to I, which is a subset of A. We have to show that there is a one-to-one correspondence between the ideals R which contains U and the ideals of the quotient ring R by U. We can easily show that f of j and g of I are ideals for j belongs to C and I belongs to D. Now we take f composition g of I. F composition g of I equal to set of all A plus U such that A plus U belongs to I, that is same as I. And G composition f of I equal to set of all A such that A plus U belongs to f of j, that is equal to set of all A such that A plus U equal to B plus U for some B belongs to j, which is a superset of j. So, if A belongs to B plus U implies A minus B belongs to U, which is a subset of j. This implies A equal to B plus j. This implies A belongs to j. Hence, we say that f composition g of j equal to g composition f of j equal to j. Hence, f and g are bijection. In this session, we had discussed about homomorphism briefly. First, we had started this session with describing about homomorphism and kernel of homomorphism with examples. And then we moved to quotient rings. Moreover, we had discussed the relation between the quotient rings and homomorphism in the name of isomorphism theorems. Now we conclude this session here. I hope you enjoy this session. We will meet in the next session. Thank you.